Okay, I'm assuming you can all hear me out there. We'll go ahead and get started. Um, so we are in our last module now, and so we have 6 lectures left for this module 5. Your final exam in this course is on November 23rd. It's in the same format in Canvas. So it's going to encompass chapters 8 and 9, which deal with alkenes and alkynes. So that's the final 2 functional groups that we're going to talk about this semester. And so what we're going to do is lead off this module with the synthesis of alkenes using elimination reactions, and then we're going to transition into the addition reactions of those alkenes, and how we can take alkenes to alkynes and then make higher substituted alkynes. So that's where we're going for the rest of the semester. You have 2 homework sets left, your exam 5, and then 2 professional development activities. So let's look at this slide here that's already up. So this is called elimination. And this is the competing process with substitution. So really, in this semester, we've learned a couple mechanism types. Substitution and elimination are 2 major ones. And of those, there's bimolecular and unimolecular processes. So let me write that down so I don't forget. Unimolecular. And again, that has to do with the kinetics of the reaction. So let's look at this general substrate here, what I've shown in the center here, because that's what we're going to start with, and that's going to sort of give us a flow chart of how we decide what sort of mechanism is happening. So I'm calling this carbon the alpha carbon, and it's bearing the leaving group X. Any carbon bonded to that is called a beta carbon. So I'm only specifically showing 1, but you can have up to 2, 3. You can have 1, 2, 3 possible beta carbons, and they can all be different, and you should sort of designate them as such. So again, I'm only showing 1, and I'm only showing 1 hydrogen of that beta carbon. So what we saw so far in an SN2 process, so substitution, nucleophilic, bimolecular. So if we have something I'm going to call nucleophile, and then a metal cation, which is balancing out the negative charge. So what can happen in this case is the nucleophile can attack the alpha carbon bearing the leaving group. That leaves, and then you get substitution. So again, you're substituting the X group, the leaving group, for the nucleophile, and so consider all the things that happen in an SN2 reaction. So depending on the classification of this X group, this leaving group, that it can ionize. Remember, if this is tertiary, this can ionize. So what I'm going to show now is sort of the SN1, the unimolecular process, and then over here to the right, I'm going to show the competing processes with substitution. So as this arrow shows, if this group ionizes, we get a carbocation. And so then what can happen is SN1. So again, if you form a stabilized carbocation, you're ionizing. And then the nucleophile, which is typically a weak nucleophile. So maybe a way I can show that is sort of like NuH. So something that's neutral. So this would be like an alcohol or an acid. So what we end up with now is a substitution where you would lose this proton. Again, if this was an alcohol, you would lose that. So you're doing substitution of the leaving group for that nucleophile. Again, the 2 and the 1 refer to the kinetics, either bimolecular or unimolecular. Now what we're going to consider moving forward is the nature of the nucleophile. So whether this species acts as a nucleophile to form a carbon-carbon bond or carbon heteroatom bond, or if this thing is acting as a base. And so this is where you're going to need to look at the reagents and ask yourself the question, is this a nucleophile or a base? The difference between those is that the action of a base is to abstract a proton. So what I'm going to write for this is just, so here I'll write E2. So that stands for bimolecular elimination. And in this case, I'm going to put instead of nucleophile, I'm just going to put base minus, then metal cation plus. So I'm just doing that to sort of differentiate nucleophile from base. Again, the base abstracts a proton. That's its action. And in an elimination, the base will abstract a proton from the beta carbon. So that's why you need to identify what the beta carbons are. So this one is directly attached to the alpha carbon, which is bearing the leaving group. This, now instead of this forming a bond to a carbon, it's abstracting a hydrogen. So that's the first arrow that's pushed. So we're forming a base hydrogen bond. We have to break the existing CH bond. And now what's happening is you're forming a pi bond between alpha and beta, and then the leaving group is leaving. So once you do that, you end up with an alkene. You end up with the coproducts of M plus X minus, and then the conjugate acid of that base. So again, just to talk through this, our starting substrate, we have an alpha carbon bearing a leaving group, we have a beta carbon bearing a hydrogen. So in a bimolecular elimination, this species is a base which abstracts a proton. We're cleaving this bond, we're making a pi bond, and then we're breaking that bond. So we're ending up with an alkene. These two carbons, alpha and beta, go from sp3 to sp2. So now there's issues where we have to determine, for example, what beta carbon is the hydrogen being abstracted from. So that's an issue we have to determine, because you can end up with different types of alkenes. So again, this is elimination bimolecular, meaning the rate depends on the concentration of the base and the substrate. If this ionizes, we can get into unimolecular elimination. So again, this is contingent upon the nature of what this base is. And so that's what you need to understand. Blakely, what's your question? So a bimolecular process does not become this. You have to look at this substrate and determine what is the classification of the carbon bearing the leaving group. If it's methyl primary or secondary, it will undergo bimolecular. If it's tertiary or secondary, it ionizes to undergo unimolecular. You're making your decision based on categorizing this. This does not become this. So getting back to the unimolecular manifold, the difference between E2, E1, you classify the substrate. If X ionizes to the carbocation, and now look at the nature of this. Here you have a metal cation plus a negatively charged base. Here you have something neutral. Again, this is going to be something like solvent. It's like ethanol, just straight ethanol. So when that happens, the ethanol can act as the base. Again, we're forming an alkene. So in this case, you would end up with something like B, H, we just balance out the charges there. Again, this may be a little confusing, so we're gonna learn what these things actually are and how do we differentiate this from this, just to give you a preview of that. These are things like sodium ethoxide. These would be things just like ethanol. Someone was saying something?
I know briefly asked about the arrow. I'm kind of confused about that as well. Why did you write an arrow saying ionization effects? Can you kind of elaborate on that a little bit?
So let me, I know there's a lot of arrows up here right now, so let me just talk through it again. If it's not clear, I'll go to another slide and redraw it. So what you have to consider now is, as a student learning this, you are given a substrate, and you have to determine, okay, a decision point. Based on the substrate, is it going substitution or elimination? And you have to determine, of those, is it bimolecular or is it unimolecular? So if this substrate, if you're starting with something that is tertiary, the X group ionizes, so that gets you automatically into a unimolecular process. So if it's methyl primary secondary, it's most likely going to be bimolecular. So what I'm showing here is just the manifold of possible things that can happen. So again, for example, think about what you learned for SN1, SN2 versus SN1. How did you know it went this way versus this way? Is that clear?
Not really.
Not really? Okay. Let me on this slide, I'm showing you a general substrate. These can be anything. This, and this can be anything. I'm just showing you the necessary features that need to be there for SN2 versus E2, ionization SN1, E1. I feel like I'm being trolled right now. Am I being trolled? M is a metal. It's a metal cation that is balancing out this negative charge. Sodium ethoxide, sodium whatever. This has to be there to balance that charge because you cannot have a naked whatever existing in real life. Is that clear? If it's not clear, I suggest you crack open your, put up another slide here. So when you look at these two compounds, I'm going to say A and B just so we can refer to them maybe in the chat as well. So if I ask you a question, A versus B, which one undergoes SN2 reactions? So Blakely, I really don't like what you're writing in the chat. A bimolecular process does not become a unimolecular process. Again, you're figuring out which process is occurring. One is not going into the other. So B does SN2. Why does it do SN2? Because it's primary. So A does what? So that's essentially what I was showing you on the prior slide in a very general form. So when you're diagnosing these substrates, you're making a decision at that point. Now what we are learning is what is the nature of the nucleophile. Is it a nucleophile or a base? If it is a nucleophile, then it's going to do substitution. If it's a base, it's doing elimination. And that's what you have to learn as the student, is the difference in these reagents. If it gets ionized, then yes, it's going through a unimolecular process. And Chem book and review it. All right, so let's talk about the mechanism of bimolecular elimination. So again, you need to understand when we talk about bimolecular versus unimolecular, that's the concentration of the reagents in the rate limiting step. So this is called E2, so elimination bimolecular. So what we are diagnosing at this point is we have a substrate bearing a leaving group, which is bromine. We know that's a good leaving group. So how do we know that it's elimination versus substitution? You're looking at what is this? We have a sodium cation balancing out the negative charge of ethoxide. So the question you're probably asking is how do you know nucleophile versus base? And again, this is probably something that's just easiest to memorize. Bases are typically substances that have have a negative charge on a heteroatom like this. So things like ethoxide, methoxide are typically acting as bases. And again, that is the difference. A base abstracts a hydrogen. So when we look at this substrate, the first thing you need to do is identify the carbon bearing the leaving group. And we want to call that the alpha carbon. And this is just strictly a convention to help us talk about how the mechanism of elimination proceeds. So of that alpha carbon, how many beta carbons do you see? So there are 2 beta carbons. Are the beta carbons the same? Are they identical? So no, they are not. So here is a beta carbon, and here is a beta carbon. So I want to differentiate them, and this is just completely arbitrary. I'm just going to call this beta prime. I just did that so we can talk about beta versus beta prime if we're talking about the location in the molecule. The base is going to abstract a hydrogen from a beta carbon. Now what I've shown you here is that you get a major product, a minor product, and trace product. So this is a product distribution. Now we want to understand in learning this, why do you get a distribution and not one thing? And so as you've sort of seen in the build-up so far in this this course and this semester, is that there are many factors that go into play in a mechanism. And so that what makes this course a little bit difficult is it's not just a slam dunk of this, but you're also getting this and this, and you have to explain why. So this is major, this is minor, this is trace. Just so we put some names to this, what is the name of the major product? And I'll write it under here after you write it in the chat. So we have trans 2-butene, and then what is the name of this minor one that's next to it? So this is cis 2-butene. And then finally the trace product is 1-butene. So there's some other terminology in the chat. Let me just show you what that is as well. So trans, cis, trans is E, cis is Z. So let me ask you this question. Beta prime is not equal to beta. So beta prime has beta prime has 2 hydrogens, beta has 3. That's just from simple observation. This major product results from deprotonation of which beta carbon? Beta or beta prime? So it's resulting from beta prime, but how do we make sense of that? If beta prime has 2 and this has 3, statistically, the base should abstract more protons from the beta carbon because there's 3 of those versus 2 of those. So what can we say about this product distribution so far without sort of knowing the mechanism? When you look at these alkenes, what differentiates them? Just observations, looking at them. So the location of the pi bond, Ian says trans alkenes are more stable. So how do these two differ from this one? These two differ from that one. So Aiden says the more substituted carbon is preferred to lose a hydrogen. Yes, that's true. Blakely says the pi bond in the middle. So let's sort of elevate the language here. when you're considering the two sp2 hybridized carbons of the alkene, this major one has 1, 2 substituents. So does this one, 1, 2, and this only has 1. So just from our observations and what these words mean, we can make this claim. Disubstituted alkenes are more stable than monosubstituted, because we're forming this, which is disubstituted, as the major product in preference to a monosubstituted. Now between these two disubstituted, as was alluded in the chat, the trans is more stable than the cis. Can you think of a reason why that is? So remember, I believe it was chapter 4. Go ahead, put those hydrogens in. So in the transalkene, these two large groups are opposite one another, but they're on the same side as something small. In the cisalkene, the large groups are on the same side. And what you have to remember is that these methyl groups take up space. And so if they're both on the same side of the alkene, they're sort of banging into one another, and that leads to strain. And so the reason that this is formed versus that is due to a strain argument. This is less strained than this. So what I want to talk about now is the actual arrow pushing of this in consideration of some trajectory. So I'm going to draw the starting material as such. So I've picked out those 4 atoms, H, C, C, B, R, because they are needed in basically the mechanism. So what I'm going to do now is put in the remaining groups. So I've drawn that very suggestively. This H, this C, this Br, they are all in the plane of this, this whiteboard. So knowing what you know from a Newman projection, what is the angle between the H in the bromine So it's 180 degrees. And so what I want to do just below this is draw that with the perspective of your eyeball here looking down this bond. Again, the Newman projection is looking down a sigma bond. And so when we do that, that's your front carbon. This hydrogen is the hydrogen that's down. This hydrogen is the one to the right. Again, here it's coming out towards you. Here it's to the right. The methyl group is back. Here it's to the left. There's your rear carbon. Now your bromine is up. This methyl group is here. This hydrogen is here. So here is that angle we were just asking about, HCCBR. It's 180 degrees. And so that is a necessary requirement for all elimination reactions. So here we have our base. Sodium ethoxide. It's abstracting that hydrogen. We're forming that pi bond, and then this is leaving. So we're proceeding through a transition state for elimination. This bond is partially breaking. We're partially forming a pi bond. And this bond is partially breaking as well. So that's our transition state. Again, this is developing a negative charge. We're partially forming that OH bond. And so I'm going to put some stereochemistry wedge dash in this product representation. So those bonds are going away from you, and then these bonds are coming out towards you. So that's meant to indicate that the alkene is sort of perpendicular to the whiteboard. So our byproducts here are sodium bromide and ethanol. So I've shown you the trans being the major. And if we go back to this Newman projection, you can understand that because the methyl groups are 180 degrees opposite to one another. So if we were to represent this in the Newman projection, sodium ethoxide, you would see from that, if we just drew the Newman projection, you have to retain there's your front carbon. You have to retain those orientations of the substituents. So that would be a Newman representation if you were looking down the CC pi bond axis. So you see that those substituents are trans. So I've left this space empty, but I want to fill it, and I want to explain to you why it is absolutely necessary that you have this 180 degrees dihedral angle. And that involves looking at the molecular orbitals. So let me just point out that is the sigma bond. That's a molecular orbital of CH. That's the bond. This is the sigma bond of CBr. And so what is happening that we recall every time there's a sigma bonding orbital, there's a sigma anti-bonding orbital. So when this hydrogen gets abstracted, these two electrons are immediately disposed to go into this anti-bonding orbital, which results in the formation of that pi bond. These electrons then leave to form the bromide anion. So this is why you need this orientation, is so that this sigma bond overlaps with this anti-bonding orbital and these electrons can go right into it. So again, that's this action here. When the base is abstracting that hydrogen, when this bond breaks, these electrons go into the anti-bonding orbital, and then this bond cleaves, and you get your inorganic byproduct while forming your pi bond. Any questions on the explanation of the major product so far? So let me just talk about how you form the minor in trace products. So again, the minor product results from deprotonation of the beta prime carbon as well, but it's now deprotonating the other CH bond. So let me let's just look at the Newman projection first. So the Newman projection I had written on the other page. So that Newman projection led to the major product. Now if we do a bond rotation, I'm going to leave the back carbon the same, and I'm going to rotate the front carbon, because what we need to do, again, this is our beta prime CH2, so that's this CH2 group here. When this gets deprotonated, that's when we get to the major. If we rotate around so that this is now down here and we have that 180-degree relationship, you'll see how the minor forms and why it is the minor and not the major. So let's do the rotation. That's skill number 1. I'm not changing the back carbon at all. The front carbon I'm going to rotate this way. This methyl group's going to go over here. This hydrogen's going to go down. This hydrogen's going to go over here. So now what is what is the issue that you see in this Newman projection that you would say this is a minor conformer compared to this? Again, the reason that this becomes the major product is because this conformation is more preferred. Why is this less preferred than that? So you have these gauche methyl groups. So remember that that's an energy penalty that you have to pay in that conformation. We were calling that, I believe, 3.8 kilojoules per mole. So again, this conformation is higher in energy than this. So when we do this elimination, you can now see that that forms the cis product. Both of these methyl groups are on the same side. These methyl groups are on the same side now. So whenever you're doing an elimination reaction, you really want to put things into a Newman projection because it will help you visualize geometry that's formed trans versus cis. So now the trace product is coming from deprotonation of beta. So again, this is beta. You're now looking down this Newman projection. So in the front, you have a methyl group. Then in the back, that's your alpha carbon. It really doesn't matter which one of these hydrogens gets deprotonated because you're ending up with a mono-substituted alkene and there's no cis or trans geometry. So as we saw in the prior slide, we observed that the more substituted the carbon is, that leads to a more substituted alkene. So the alkene stability trend, which we'll write down here and we'll talk about probably in the next chat session, is the following. So if R1, 2, 3, and 4 are all carbon, that's tetrasubstituted. Again, R1, R2, R3 are all carbon, that's trisubstituted. Then you can get into various disubstituted. So that would be trans. That would be cis. You could have R1, R2 on the same carbon. So those are all disubstituted. And then those are more stable than monosubstituted. So again, alkene stability, tetra is greater than tri, is greater than di, it's greater than mono. To help you figure out, again, when you look at your beta carbons, the more substituted the beta carbon is, that leads to the more substituted alkene after it's deprotonated. Any questions before we move on to our next topic regarding alkene stability or alkene formation? So again, the big picture of this module is right now you're learning how to form alkenes through elimination. And the formation of an alkene is what is going to generate a nucleophile that we can then treat with other electrophiles and do another type of reaction called an addition reaction. So in this slide, what we're going to do is look at a bulky base. And so again, this is where you're going to have to really pay attention to the nature of the nucleophile or base. Now, when it's a base, what is the size of that base? So we're talking about like steric size. So things like van der Waal radii. So let's look at, again, our starting material here. We have actually, I'm going to change this slightly. I'm going to use this substrate. This is our alpha carbon. We have two methyl groups, beta, beta, those are the same. This methylene, that's beta prime. So here's our metal potassium. Now the base that we are using, it's an alkoxide base called potassium tert butoxide. Potassium tertiary butoxide. Our solvent is going to be tert butanol. So typically with these elimination reactions, you're using the base and then its conjugate acid. So that's a clue that it's going to be an elimination. So this is what is referred to potassium tert butoxide. This is a bulky base. You have a tertiary carbon bearing 1, 2, 3 methyl groups. This is a big base. So the Hoffman rule, as opposed to what we just saw, the Hoffman will always deprotonate from the less substituted carbon, the less substituted beta carbon. And the reason for that is in beta versus beta prime, these are more accessible to this base, which is big. Beta prime hydrogens are hindered. So if this is really big, this base has a harder time seeing or finding these. So this goes after the more accessible hydrogens. So our products from this, this is going to be the major. The minor is going to be the following. So again, what we have to understand is that in comparison of these two products, this resulting from deprotonation of the beta carbon, even though it's only di-substituted, it's major because this base is too bulky to deprotonate from beta prime. So even though this is 1, 2, 3 tri-substituted and it's more stable in terms of alkene stability, it's the minor product because the base has a harder time abstracting these hydrogens. So how can we rationalize that? If we look at, say, a Newman projection down this bond versus the Newman projection down that bond, we'll sort of see what that argument means. So those are the relevant Newman projections. And as you can see, this Newman projection results from looking down this bond. This Newman projection results from looking down this bond. So you see these hydrogens are more accessible for a large base coming in versus these, which have to contend with all these methyl groups hindering those hydrogens. So how do you know when the base is bulky? Since you're not really going to be doing this for a living, really the only one you need to know is potassium tertbutoxide is the major bulky base for organic chemistry. So if it has the tertbutoxide, that's what we consider bulky. The other ones, as we saw on the prior slide, like methoxide, ethoxide, those are small. Any further questions on the elimination mechanism so far? This is ethyl, CH2CH3. This is CH3CH3CH3. So finishing up today's lecture on our last 5 or 6 minutes here, I'd like to talk about elimination and cyclic systems. So again, for elimination, you must have the hydrogen, carbon leaving group at 180 degrees. So when you're given a cyclic system, that's basically telling you you have to convert it to a chair. And then you have to look at both conformations of that chair. You can't just look at one, you have to look at both. So here is a system. We basically have a methyl cyclohexane with O-tosyl, that's the leaving group. We're treating with potassium tertbutoxide and dimethyl sulfoxide at 55 degrees. And I'm telling you, you're only forming this and not that. So we want to explain why. Let's put in our alpha carbon. It's the carbon bearing the leaving group. We have beta and we have beta prime. So what I'm going to do first is convert that flat cyclohexane to a chair. So the the methyl group is up. So I'm going to put that methyl group here. That's up. The hydrogen bonded to it, that's down. So that was your beta prime. Your alpha carbon is bearing the tosyl group down, so that has to be equatorial here. That hydrogen there is up. So here's your alpha. Then your other beta is just simply 2 hydrogens. So that's just going behind that group. So now what I'm going to do with the red highlighter is I'm just going to highlight all the beta hydrogens. So you have 3 possibilities of hydrogens that can be deprotonated. And you must obey this. HCCX has to be 180 degrees. Looking at this conformation, do you see a dihedral angle between beta or beta prime where HCC tosylate is 180 degrees? Put another way, HA, HB, or HC, can any of those be deprotonated now to do an elimination? So the answer is no, because to get to this scenario in a cyclohexane or chair, these H and C both must be axial. So we have to do a chair flip. So again, when we do a chair flip, things that are equatorial become axial. Things that are axial become equatorial. So now of those 3, HA, HB, HC, which one has the correct orientation to do the elimination? HA, HB, or HC? So Hannah, at first I thought you were laughing when you put ha, but yeah, I understand now. It's HA. As Mac has corroborated. So HA is the correct. So let me just outline that 180 degree relationship in green. So there's your 180 degree relationship. Let me throw that into a Newman projection just real quick in the last minute so you can see. If we're looking straight down that bond, OTS is down. Here's HB. Here's HA. You have the rest of the ring going that way. So this is a double barrel Newman projection. So there is that, again, relationship of 180 degrees as we see. That's what's required. And so this is why you only get elimination to form that and not this. So when you're doing eliminations in chair or cyclohexanes, you have to convert it to a chair and then do this analysis.